Today, we come to the chapter of collision. Once again, we shall solve some problems of your textbook of C Verma. Uh, I'll straight come to the problem number 19 because problems before this are too preliminary. What this problem 19 says, a man of mass M having a bag of mass small m slips from the roof of a tall building of a height h and starts falling vertically. So, for the diagram, suppose this is the man which is bag of mass, total mass is m plus small m, and he starts dropping vertically and starts dropping vertically. Say this is the ground. Say this is the ground. And it is said that the height of this building is capital H. Then what happens? When at a height H from the ground, that means something happened when he was at a height H from the ground. Say at this point, and height of this point is small h from the ground. From the ground. When the man is here, what he notices that there is a pond at a horizontal distance x. That means, let us say on this side, at a distance x, there is a pond. Distance is x. So definitely he would like to fall in the pond, not on the ground. And how he can do this? What he did, the bag horizontally in the direction opposite the pond. That means this man throws the bag horizontally, that is small m, in the direction opposite the bag. Now, the problem basically is not very difficult. And it is considered that you can consider this way, that a mass of total mass, that a body of total mass of m plus m is broken into two parts. Small m part is given a velocity in this direction, and definitely capital M part will go in this direction. That means if the man can throw the bag forcefully enough in opposite direction, the man will have a horizontal force or horizontal momentum. So at this point, the man will have a vertical attraction due to gravity as well as horizontal, so he will start falling in a parabolic path. If the man lands at the edge of the pond, the man just lands at the edge of the pond here, distance x. He just lands at the edge of the pond. Find the minimum horizontal velocity imparted to the bag. Then what velocity he must impart to the bag? This they want to know, right? So let this velocity is v, and let this velocity of the man is capital V. Right? So the bag also will fall in a parabolic path to the ground somewhere here. In the second part, it asks where will the bag land? That means if this distance is y, the second question wants you to find out y also. Now let us start doing the work. First, do a small arithmetic here. The man with the horizontal component of velocity capital V, the man just reaches the point. And let us say this time is t. So say the man reaches the ground, ground from, let us give some name of these points. Let us say this name is A, this is B, and this is G, the ground. So man reaches the ground from B is equal to A, this time is T. Then his horizontal velocity was capital V. So capital V into small t is equal to x. There is no doubt in that. Then V into small t is equal to x. Right? Or you can write or capital V is equal to x by time t. Also, from the principle of conservation of momentum, the principle of conservation of momentum of conservation of momentum. Now look, the man and the bag, when they dropped from the top, they had no horizontal velocity. So they had no horizontal component of momentum. Now they have separate horizontal component of momentum, horizontal component of velocities in opposite direction. So the momentum in two opposite direction has to be same. So we write, so V into capital M, that is momentum of the man, must be equal to small v into small m, momentum of the bag. From here, what we find, I want to write one more line here. That's why. From here, what we find, with capital, from here we find small v is equal to capital M by small m into capital V. Capital M by small m into capital V, which is equal to capital M by small m into. So this is one observation. The velocity of the bag is capital M by small m multiplied by t. That means capital M and small m is given. T is the time he needs to fall from point B to ground. This time we have to find out. That is the point. How we find out this time? Right? Here, what we do, we come back to this point. If this is capital H from here, from A to ground is capital H, and B to ground is small h, then obviously this distance is equal to capital H minus small h. Right? Also, let us consider the time of fall. say time of fall A to ground G, say time of fall from A to ground G is equal to T1. That means from A to ground G, it falls in the time T1. Then we can use the formula of kinematics, where we can easily write the height h is equal to, the formula is h equal to u square plus half gt1 square. The u is 0 because the man started falling from rest, plus half g square. From here we get is equal to 2h by g under root 2. Similarly, say time to fall from A to B equal to T2. Let us say this time is, so that we can once again find T2 by applying the same kinematics formula, because this side is capital H minus small h is known. So capital H minus small h will be equal to similarly 0 plus half g T2. From here we get T2 is equal to h minus small h 2 into minus small h divided by g capital H divided by g whole under. So we have got T1 and T2. So we can easily find T, the time of fall from B to G, by just by subtracting these two figures. So T is equal to T1 minus T2. One is under root 2h by g, and T2 is under root minus small h by minus small h by g. This is equal to, we take under root 2 by g outside a bracket, and this becomes root h minus root of capital H minus small h. Now we go to this formula of equation 1. Say, let us say we give this a name, formula name of equation 1. One, what we get? V is equal to capital M by small m into T, and capital M into small m T. Here, there was a V equal to equal to x by, from here we get t is equal to capital M by small m, capital V. There was a mistake here. Shall remove it. There was a mistake here. From here we get small v equal to capital M by small m into capital V, which is equal to capital M by small m, and capital V is x by t. So t, and this is say equation 1. So this is capital M by small m into x by t into x, and that divided by t. So root g will go to the numerator, root 2 the denominator, and this thing will come in the denominator, minus root h minus root over capital H minus small h. So this is the velocity. This is one answer. That is the find the minimum horizontal velocity imparted to the bag. This is the minimum horizontal velocity. If the man throws the bag with further more force, that means if small v is more than this value, then the man will go further into the middle of the pond. But the problem says he just lands at the edge of the pond, for which he has to give the minimum velocity. Also, now coming to the second part, this is first part. Second part is the part B. Second part is the part B, where it says, where will the bag land? Y. Y is equal to definitely small v multiplied by small v multiplied by this time t. Small v multiplied by this time t. And we have already got here small v multiplied by this time t is from this equation, we write from equation 1, small v into time t, y is equal to small v into t is equal to capital M by small m, capital M by small m into x. So this is the answer to the second part. Okay. Now we shall go to the next problem.